Section 1.7 is inverse functions. So if you remember from the section on functions, 1.3, we know that functions can be represented by a set of ordered pairs. For example, if I have the function f of x equals x plus 4 from the set A, which is 1, 2, 3, 4, to the set B, which is 5, 6, 7, 8, I can write this function as a set of ordered pairs, 1 to 5. 1 plus 4 gets me 5. 2, 6. 2 plus 4 gets me 6, and so on. By interchanging the input and the output, or swapping my x and y values, I can form the inverse function, which we denote as, it looks like this f with the little -1 here. We don't call it f to the -1, we call it f inverse. So it's a function from the set of b to a, notice I'm going a different direction, and I can write it as, I just flip-flop all the y's. So I went, or the x's and y's, so from 1, 5, I went to 5, 1, 2, 6, I went to 6, 2. Okay, that's my inverse. I just flip-flop the x's and the y's. So if you think about that, and you think about what all the x's are called and what all the y's are called, the domain of the function is equal to the range of the inverse and vice versa. And the function and its inverse have this effect of undoing each other. So what's done in one is undone in the other. If you look at this picture here, they show us, well, our function was x plus 4, and so the inverse was x minus 4. What was done in one, the adding of the 4, is undone in the other, the subtraction of the 4. And if you also notice, just plain old x is my domain of f, and that is the range of f inverse. So the range of f is the domain of f inverse, right? I just flip-flop my x's and y's. So when we undo these functions, we should get back to our identity function. Our identity function is just x. So if you remember 1.6, we did an example where we composed two functions and the values were equal, they were both x. That isn't always the case, but it is the case that if it happens, they are inverses. So this will only happen if the two functions are inverses. Knowing this quality, we're going to use that to prove when we have inverses, or disprove something that they aren't inverses. Just informally, we can use our prior knowledge to come up with an inverse. So if it says find the inverse function of f of x equals 4x, well, think about this. I'm multiplying by 4, so my inverse function needs to undo a multiplication of 4, which would be a division of 4, which is the same thing as multiplying by a fourth. So whatever one you wanted to do here is fine. Okay, I'm going to show you a way to find the inverse when they're a little more difficult than this. But you also, and this is part of finding the inverse, and we're going to do this every time, is we're going to have to verify that they are actually inverses of each other. And this is what I was talking about. If I take the function, compose it with its inverse, and the inverse and compose it with the function, I should always get them both to be equal to x. That would prove that they're inverses of each other. So I'm going to start with this. I'm going to start with the function composed with the inverse, meaning I'm going to take my function, which is 4x, and anywhere I see an x, I'm going to plug in my inverse, which is x over 4. So instead of this x, I get rid of it, and I plug in this x divided by 4. What happens here when I plug in the inverse is that the 4 on the top and the 4 on the bottom cancel. I'm just left with x. And so now I need to do the inverse composed with the function. And so my inverse is normally x over 4, but instead of that x, I'm going to plug in the function 4x. So I get rid of this x. Instead, I plug in my original function, which was 4 times x. And what happens is, again, the 4's cancel out. I'm just left with an x. This proves inverses. Inverses of each other. So that's what we're looking for. This is a very simple example. We're going to do ones that are a little more complex. The next example here is exactly like the one above. The inverse is just different, but it's the same process for comparing. If you look down here, it says important. We need to know that f inverse is not equal to 1 over f of x. So if you have normally something like this, 2 to the negative third power, it's really 1 over 2 to the third. That's our negative exponent rule. This, though, is not a negative exponent. It's a notation. It's saying this is an inverse. Okay, so say f inverse, that's what I'm talking about here, as opposed to 1 over the function f of x. They're not equal to each other. Okay, so here's our formal word definition. It says, let f and g be two functions such that f composed with g is equal to x for every x in the domain of g. Notice I left off all the, remember I was talking before about restrictions on the domain? This is saying for all the domains as limited by the original g of x domain. And g composed with f of x is equal to x for every x in the domain of f. Under these conditions, we say g is the inverse function of f. Function g is denoted by f inverse and read f inverse. So, like we just said, this is really important. This is something you want to star, make a note of, because this is how you prove inverses. If I take the inverse and plug it into the function, it gives me x. If I take the function and plug it into the inverse, it also gives me x. So whatever you want to do to make note of that, that's what you're looking for. That's how you're going to prove these inverses. The domain of f must be equal to the range of f inverse, and the range of f must be equal to the domain of f inverse. That's just a note in the future, things to be aware of, because you're just flip-flopping the x's and y's. So if they gave you a domain for f, you would know the range for f inverse. So here's a way to verify algebraically. All I would do is take f, compose it with the inverse, and what I'm hoping for, I'm verifying here. So they gave me these two functions, and I'm saying, is this equal to x? You know, I won't call it the inverse, I'm sorry, I'll call it g of x. And then I'm going to take g of x and compose it with the function, and hope that it also equals x. So I'm doing two separate questions here, basically, two parts. So I take the original function, f. I'm going to write it like this for the sake of space. And instead of the x, because it's something to the third power, minus 1, I'm going to write in this whole function. So I'm going to copy it, put it right there. And what I notice happens is the cube power and the cube root cancel each other out. And I have 2 times x plus 1 all over 2 minus 1. Next thing I notice, the 2 multiplying and the 2 dividing cancel out. I have x plus 1 minus 1. And then my 1's cancel, I'm just left with x. So f composed with g is in fact equal to x. One down to go, one to go. I have to prove them both. If one works, that's great, but I want to show the other one works as well. So now I'm going to take my original function of g, I'm going to write it again like this, so we get used to the notation and to save space. And my original function is the cube root of x plus 1 all over 2. So instead of that x, I'm going to take this whole function and plug it in over here. And what I notice again is that I have the cube root all over 2x to the third. These ones cancel each other out, so I'm just looking at 2x to the third all over 2. My 2's cancel each other out. I'm looking at the cube root of x to the third. Cube and the cube root cancel each other out. I'm just left with x. So g composed with f was also equal to x. Checks out. They are in fact inverse of each other. So that's my verification. That is all of the work. I know you're doing it in your head, but show me each step. Okay, show all the steps. Show that you're not doing shortcuts. Sometimes people find an inverse and then want it to be the, well, think they find an inverse and want it to be the inverse so badly they just fake the steps. Show that you actually are following the order of operations and canceling out properly. We're going to skip this example and the graphing. We're going to go over graphing in class. What I want to do is look at how to find an inverse algebraically. So here's what we're going to do when we're finding an inverse function algebraically. We're going to replace f of x with a y. So f of x, g of x, h of x, whatever it says, we're going to replace that with a y. Because if you think about it, when we are finding an inverse, we're swapping the roles of x and y. And now you're going to solve for the new y. And then remember what we just said about verifying inverses. You have to show f composed with the inverse is equal to x. And the inverse composed with f is also equal to x. So verifying, showing that last step is also part of it. So here's an example. If they give us this function f of x equals 5 minus 3x divided by 2, my first step is to replace f of x with a y. So I have y is equal to 3x over 2. Next up, I'm going to swap the x and y. So instead of writing an x here, I write a y. The rest of my equation stays the same, equals 5 minus 3. Instead of an x, I'm writing a y, all over 2. And now I'm going to solve for y, so I'm trying to isolate this y right here. So first thing I'm going to do is multiply both sides by 2. I have 2x is equal to 5 minus 3y. I'm going to subtract the 5 on both sides, so I have 2x minus 5 is equal to negative 3y. And then I divide both sides by negative 3. So I end up with y is equal to 2x minus 5 all over negative 3. What I just found, this new y, is my inverse function. In my mind anyways, as far as I know, I'm going to verify in a second, but this is the inverse function. This is what I'm going to use as my inverse function. So if you remember, I'm going to draw myself a little organizational chart here. I need to show that the function composed with the inverse is equal to x. And I need to show that the inverse composed with the function is equal to x. So the function composed with the inverse on the top, inverse composed with the function on the bottom. So on the top, I take the original function, and instead of an x, I plug in what I just came up with as the inverse. It's still my original, everything else is the same, right? So that I'm dividing by 2 on the bottom. Just instead of the x, I plugged in that function. So when I start, I have to look at this and think, okay, I'm multiplying by a negative 3 out front and dividing by negative 3 inside the parentheses. So I can cancel these out. And I'm just left with 5 plus 2x minus 5. I canceled the negative, so that went all over 2. Now my plus 5 and minus 5 cancel. I'm just left with 2x over 2. My 2's cancel. I'm left with x. That's what I'm looking for there. I'm now going to look at my inverse composed with the function. So I take my inverse, which was 2x minus 5 all over negative 3. And instead of an x, let me do this. I'm going to plug in my original function, which was 5 minus 3x all over 2. Remember, I still had that minus 5 on the numerator there. So I plugged this into here anywhere I saw an x. My 2's cancel out, so I have 5 minus 3x minus 5 all over negative 3. 5's cancel. I have negative 3x over negative 3. My negative 3's cancel, and I'm just left with x. That's what I want to show. I showed that the function composed of the inverse composed of the function are x. So my actual answer when they asked me to find the inverse is this. This is my inverse right here. 2x minus 5 all over negative 3. But I proved that they are in fact inverses of each other with my work on the right side of the screen. Here's another example of finding the inverse and verifying. We're going to do tons of practice with it in class because it shows up later when we talk about inverse functions.